Imagine venturing into space, beyond Earth's protective embrace, where an invisible force constantly impacts everything. This force, cosmic radiation, is a significant challenge for human spaceflight, and understanding its effects is crucial for astronaut safety. But how do we even begin to measure something so pervasive and complex? Cosmic radiation exposure is calculated through a sophisticated combination of physical measurements, advanced computational models, and biological assessments. It is not a single, simple number, but rather a dynamic estimate of the absorbed radiation dose, taking into account the type of radiation, the duration of exposure, and its potential biological impact on the human body. The core reason this calculation is so intricate stems from the nature of space radiation itself. There are two primary types: galactic cosmic rays, or GCRS, which are high-energy particles from outside our solar system, and solar particle events, or SPES, which are sudden, intense bursts of radiation from the sun. Each type consists of different particles like protons, helium nuclei, and even heavier ions, all traveling at incredible speeds. These particles interact differently with spacecraft materials and human tissue. Factors like the mission's trajectory, the spacecraft's shielding design, and the duration an astronaut spends in certain radiation environments, such as during extravehicular activities, all profoundly influence the total exposure. Therefore, scientists must account for these variables, converting the physical energy deposited by various radiation types into a standardized measure of biological risk, known as the dose equivalent. To practically determine an astronaut's exposure, scientists employ a multi-pronged approach. Before a mission, sophisticated computer models simulate the expected radiation environment along the planned flight path, considering solar activity forecasts and the shielding properties of the spacecraft. During the mission, astronauts wear personal dosimeters, small devices that continuously measure the radiation absorbed by their bodies. Additionally, area dosimeters are placed throughout the spacecraft to monitor the ambient radiation levels. These real-time measurements are then fed back into the models, allowing for adjustments and more accurate estimates of cumulative exposure. A key concept in this calculation is the quality factor, which acknowledges that different types of radiation cause varying degrees of biological damage even at the same absorbed dose. For example, a heavy ion from a galactic cosmic ray can cause more concentrated damage to DNA than a proton. Another critical consideration is the effective dose, which further refines the risk by weighting the dose based on the sensitivity of different organs and tissues to radiation. This detailed, organ-specific approach ensures a more precise assessment of an astronaut's lifetime radiation risk, allowing mission planners to enforce career limits for cumulative exposure and develop strategies like storm shelters on spacecraft to protect against intense solar particle events. Ultimately, accurately calculating cosmic radiation exposure allows space agencies to design safer spacecraft, plan healthier mission profiles, and develop protective measures, from advanced shielding materials to potential pharmaceutical interventions. This meticulous work is fundamental to pushing the boundaries of human exploration, ensuring that astronauts can venture further into our solar system with the best possible protection against the invisible forces of space.
Join us at Space Tech Insider, where innovation meets the infinite. Discover the future today.